Next method, Vogel's approximation method. This method is also known as penalty method. So Vogel's approximation method is also known as penalty method or VAM method, VAM, VAM method. The allocation is made in this method on the basis of penalties cost that would have been. So in this method, the allocations are made upon by using penalties. So we have to find out the penalty for given transportation problems to determine penalty for each row and subtracting in this method involving steps are involving three steps from the given transportation table. Determine the penalty for each row by subtracting the least unit cost in that row from the next least unit cost. So we are identifying first least cost and second least cost in the first row or second row, all the rows, and subtracting least element and second least element. So in the same row and same column also. Element and second least element in each column. So subtracting least element and second least element for column wise and row wise. The second point, identity the row, the column which the largest penalty among the different rows and columns. So after finding penalties for each and every row, so we have to take a largest penalty. So largest penalty for all the different penalties. So we can choose largest penalty for the different penalties. So for example, if there is a tie, so tie case, if the largest penalty are two elements are there. So for example, 23, 23. So in this case, tie. So 23 is the highest penalty, but two positions are there. So 23, 23. So in this case, so we can select any one. So select arbitrarily the topmost row and the extreme left column. Okay? So we can choose any one. So next point, in this row or column, identify the step B. Select the cell has the lowest unit cost. Cij denotes Xij as the basic variable for identified Xij. So in the cell Xij, the cell allocation maximum possible unit at this cell subject to the availability requirement constraints. This completely execute a row of column, ignore a row or column. Okay? So after identifying highest penalty, so in that row or column, so we can choose maximum number of allocations. So maximum number of possible number of allocations. So last point, repeat step A, C. So repeat step A and step C for the complete the all allocations. And so we are getting initial basic feasible solution. So repeating all the steps 1, 2, 3, ABC. So further we are getting initial basic feasible solution. So for example, so find the initial basic feasible solution for the following transportation problem using Vogel's approximation method, and also find the cost of the transportation. So here is given table and so table. So transportation table. So these are the cost matrix. So this is the cost matrix D1, D2, D3, D4, D5, and O1, O2, O3. So these are the availability sign. These are the requirements. So first we have to verify The given transportation table is balanced transportation or unbalanced transportation. In case the given transportation table is unbalanced, to make it as balanced transportation problem, and after we can do Vogel's approximation method. So otherwise, so directly we can do. So requirements. The total requirements equals to 300, 100 plus 70 plus 50, so 40, 40. The sum of all requirements, so the sum of all requirements is equals to 300, and the sum of all availabilities 50, 100, 150. The sum of all availabilities equals to 300. So requirements is equals to availabilities. So requirements equals to availabilities. The sum of requirements is equals to sum of all availabilities. So therefore, the given transportation problem is balanced transportation problem. In case the sum of availabilities is not is equals to requirements, so then we can proceed further method to convert unbalanced assignment problem to unbalanced transportation problem to balanced transportation problem. Is clear? So these are the requirements and availabilities are equal. So clearly the given transportation problem is balanced transportation problem. Okay. So next further we have to find out penalties. So we have to find out penalties for each and every row and column. So first one, so in first row O1. So in first row O1, so first least element is 1. In entire row, in O1 row, entire row, so first least element is 1 and the second least element is 9. The first least element is 1 and the second least element is 9. So penalty is nothing but second least element minus first least element. First row. So penalty is nothing but second least element minus first least element is equals to 8. So penalty for first row is 8. Is clear? So here we can see, so 0, O1 row penalty is 8. Okay. So in first row we can identify least element and the second least element. So second least element minus first least element. So we are getting penalty for first row. So similarly, the second row. So second row also, so this is O2 row. So in O2 row, so here first least element is 1. So first least element is 1 and the second least element is 12. So 12 minus 1 is equals to, so 11. So penalty for second row is 11. So here, so we can see, so penalty for, so second row is 11. So next third row. So in third row, so 14, 33, 1, 23, 26. The first least element is 1 and the next least element is 14. So 14 minus 1 is equals to 13. So second least element minus first least element is equals to 13. So penalty for third row is 13. So 8, 11, 13 are the penalties for first and second and third rows in the given transportation problem. So next, so similarly, we have to find out each column wise. So column wise also penalties. So first the D1 column. So D1 column. So in D1 column, so 1, 24, 14 are 3 elements are there. So in D1 column, so first least element is 1 and the second least element is 14. So 14 minus 1 is 13. So D1 row, D1 column penalty is 13. Is clear? So first column penalty 14 minus 1 is equals to 13. So next, similarly, so D2 column. So D2 column 9, 12, 33. So first least element is 9 and the second least element is 12. So penalty, so 12 minus 9. So 3 is the penalty for second column. So next, third column. So third column 13, 6, 1. D3 column. So 13, 16, 1. So in this first least element is 1 and the second least element is 13. So 13 minus 1 is equals to 12. So this third row. So third column. So next D4. So D4, in D4, 36, 20, 23. So these are the three cost elements in D4 column. So here first least element is 20 and so second least element is 23. So 20 minus 23 is equals to 3. So we are taking only positive numbers. So 3. So 23 minus 20. So second least element minus first least element. So 3 is the penalty for next row. So next D5. So D5 penalty is 25. 51, 1, 26. Here 26 minus 1 is equals to 25. Next penalty. You know? So this is the penalties for each row and column. So first we have to find out in Vogel's approximation method. So we have to find out penalties for each row and column also. First row, first column like this. So next allocations. Allocations. So next here. The question is mistake is there. Printing mistake is there. So here D4 column is no. This is mistake. Question mistake this one in test book. So table 7.6, there is no D5 column. So you can eliminate D5 column. This is extra column. So in question O1, O2, O3 and D1, D2, D3, D4. So you can see previous questions also. There is no D5. So this is extra column by printing mistake. So these are the penalties. So you can see here previous. So this is the okay. So next, the highest penalty. In this penalties, highest penalty is 13. So here 13 is there. Here also 13 is there. So we can summarize. So we can take 13. So in first column, so least element 1, 24, 14. So three elements are there. So first element is least. 1 is the least element. So at cell 1 comma 1, so we can allocate row wise. So row wise is 50 availabilities. So column wise is 100. So minimum of 50 comma 100. So availability is equals to requirements. So minimum of 50 comma 100 is equals to, so 50 is minimum. So you can allocate 50 in the cell 1 comma 1. So next, so cell row requirement is 0. So 50 minus 50 is 0. So next, 100 minus 50 is equals to 50. So row requirement is 0. So we can cross out entire row. So similarly, we can do all columns and all rows. So finally, we are getting, so to compute penalties for each row and column in the table 7.7. Observe that so maximum penalties occur. So O3 comma D1. So O3 comma D1, the case of tie. So here 13 is equals to 13. Here tie also, so cell O1 comma D1 and also T3 comma O3 have the least unit cost transportation. Hence, allocate x11 is equals to 50, x23 is equals to 50. So is clear? So we can allocate here 50 and here allocate. So here also 50. So ignore if the first row is and third column. So that reduced transportation matrix is now written in the table 7.8. The new entries A3 is equals to 100 and A1 is equals to 50. So which is the reduced entire allocations of the made on the cell 7.8. So continue this process of allocations. So we are getting initial basic feasible solution for WAM method. Okay. So this is so next Hungarian assignment problems. Hungarian assignment algorithms. So this is the Hungarian method to find out the solution for. So this is the Hungarian method. The steps: check whether the objective function of maximization minimization type. If not, to convert one of the minimization to minimization. So first step is nothing but so given assignment problem is minimization type or maximization type. In case the given assignment problem is maximization problem, so we can convert maximization to minimization. Also check whether the cost matrix is square matrix. If it is not, make it to square matrix by adding dummy rows or columns with zero cost. So first step is nothing but so here the total first step. So the total first step in Hungarian assignment method. So in this method, first we have to verify the given transportation problem is the given problem is maximization problem or minimization problem. In case the given problem is maximization problem, so we can convert maximization to minimization. So I will explain an example. And in case the given problem is minimization, then further you can proceed uh, to verify the given assignment problem is square matrix or not. In case the given assignment problem is not a square matrix, is nothing but square matrix is nothing but the number of rows is equals to number of columns. In this case, in case rows and columns are not is equals to, we can add some dummy rows or columns. So with zero cost, like this. Here, suppose ABCD is there. In case, so this is D column is not there. So B row is not there. Here ABC, 3 rows and 4 columns. So 3 rows and 4 columns. So 3 is not is equals to 4. So in this case, so we can add a dummy row. Dummy row, so 0, each cost. Dummy row D, 0, 0, 0, 0. Okay. So we can add a dummy row. So this is nothing but balanced assignment problem. So the number of rows is not is equals to the number of columns. The number of rows is not is equals to the number of columns. In this case, this is called unbalanced assignment problem. Unbalanced assignment problem. So to make it as balanced assignment problem, so we can add some dummy row or column. In case the rows are less than columns, so we can add rows. If the columns are less than rows, so we can add columns. Is clear? So D is equals to 0, 0. This is dummy row. Each and every cost in a row in cost matrix is 0, 0, 0. Okay. So this is first point. So first point. So first point, first case is nothing but to convert minimization problem, and second case is nothing but the square matrix are balanced or unbalanced. So next, identify the smallest element of each row of the cost matrix and subtract the same from the each element in that row. So first step, step 2. So in first row, so we can identify least cost. So least element and subtracting from each and every element in that row. So as a result, you can find at least one zero element in the each row. So we can do all the rows, each and every row. So we can select least element and subtracting each and every element in that row, each and every row. As a result, you can find a zero element in each and every row. Okay? So this is so created in each and row of reduced cost matrix. So now identify the smallest element in each row, in each column of the reduced cost matrix and subtract this element from every other elements in that column. As a result of this, you can find the at least one zero element in the reduced cost matrix. So second step is nothing but, so you can the row wise. So you can choose least element in first row. Least element in first row. So subtract all the elements in that first row. You will get a zero in first row. So next, similarly, second row also we can choose second row least element and subtracting each and every element in second row. So similarly, third and fourth and fifth rows. So like this. So and also column wise also after row reduction. So row subtraction nothing but is called row reduction matrix. After row reduction, so we can do column reductions. So column reductions is nothing but, so we can choose least element in first column. After converting row reduction matrix, not a original matrix. After converting row reduction matrix, so we can choose, so we can convert column reductions. So column reductions is nothing but, so we can choose least element in first column and subtract each and every element in that column, and second column also. So second column we can select least element and subtract each and every element in that second column. So similarly third and fourth and fifth columns. You know? So this is second point. So next step 3. So with the reduced cost matrix, try for optimal assignment. Optimal assignment as follows. So after row reduction and column reduction, so we can find zero assignment. So zero assignment, so made by these three steps. So identify the rows with exactly one zero element. So first we can select one zero for each and every row. So first row, in case first row has two zeros, so we can skip the first row. In case first row has exactly one zero, so you can mark the zero. So you can mark the zero. In case two or three zeros are there, we can skip first row. So this is first step. And ensure back box in this zero like this. So put a box in the zero and element cross out all other zeros in that column. So we can do row wise. So we can cross out zeros in entire column. So in this column, so you have to zero. So cross out all the zeros like this. So zero, cross out all the zeros in entire column. So if a row has more than one zero, so leave that row and go for next row. So see clearly, in case a row has two or more zeros, so skip the row and go for next row. In case here second row is like this. So second row has only two zeros, single zero, we can mark the zero and cross out zeros in that column like this. So in this row, in this column has only one zero, cross out the zeros in that column. Okay? So next, repeat the procedure for column of reduced matrix. If there is a more than one zero in row or column and reduced matrix, choose a row or column with the minimum number of zeros arbitrary in the row or column. Thus, chosen a select a zero at random. So in case two or more zeros are there, so we can select all the rows and columns contains two or more zeros. So in this case, so we can choose anyone randomly. So we can choose anyone randomly, cross out all the zeros in that row and column. So continue this process. So until all the zeros have been entered entire assignment are classed. So we can do all the process. So for row, each row and each column, so we can allocate all the zeros and all the zeros are crossed. So this is the second point. And third point, if any reduced matrix, each row and column has one assigned zero, then the resulting assignment is optimal. So make assignment in the cell as instead zeros. Otherwise, go to step 4. So in case after marking the zeros, so we can go to next step. So in this step is nothing but in case the number of zero assignments less than n. N is nothing but order of a matrix. So number of zero assignments is less than n. So in this case, so draw the number of lines. So lines and ticking and lining. So next, draw the number of lines equal to the number of assignments made in the step 4. So as to cover all the zeros as follows. So mark the row in which no assignment is made. So first, tick the row. Tick the row. So which row has no zero assignment? So which row has no zero assignment? So next, the second point is nothing but examine the marked row. If any zero cell occur in this rows, mark the column containing the zero cell. So after ticking row, in that row, any crossed zeros are there. In that row, any crossed zeros are there. So you can mark that column wise. Okay? So next, mark the rows which are not already marked by which have assignment in marked columns. So repeat step 1 to step 2, 3 until the chain of marking is completed. So draw the straight lines passing through unmarked rows and marked columns. So this is important point. Draw the lines unticked rows and ticked columns, unmarked rows and marked columns. So first, last point. Okay. In case the ticking and drying is occurs only the number of allocations is less than order of a matrix. The number of allocations is less than order of matrix. In this case, you can follow the step 4 for ticking and drawing of lines. So next step 5. If the minimum number of lines drawn is equals to the order of the cost matrix, then the optimal solution is achieved by the arbitrary allocations in the position of 0 not crossed in the step 4. If not, go to step 6. Okay, so it's clearly the number of zeros are equals to the number of allocations. In this case, we are not going to step 4. Okay, further, so examine those elements that are not covered by a line. Identify smallest these elements and so subtracting from all the elements that do not have a line passing through them. Now add this smallest element to every element in that point of intersection of lines. So point of intersection of lines we can adding and subtracting from remaining elements. So keep all the elements already crossed by the lines unchanged. Okay. So this is the process to finding assignment problem of Hungarian assignment algorithm. So this is Hungarian assignment algorithm. Example. A departmental store has four sales girls that can be performed four distinct jobs. So only one girl can handle a one job is given time. The cost of assignment each girl to each of the job is given below, given following table. So make a assignment of one job to one girl, so such that the total cost of assignment is minimum. So here is given. So sales girl sign jobs. So sales sign jobs. So here person sign jobs are there. So we can choose one person to so we can choose one person to one job. So the A can do all jobs. A person can do first job, second job, third job, fourth job. So B person also we can do. So first, second, third, fourth, C also, D also. So A, B, C, D, all girls can do all jobs. So but the process is nothing but the total cost of assignment is minimum. So we can find out so which girl is suitable for 1 to 3 job and the total assignment cost is minimum. You know, so we have to find out the total assignment cost is minimum. So solution. Observe here that is that this is balanced problem. So first we can identify so given the given problem is minimization or maximization. So here minimization problem. So this is minimum clearly is given minimization problem. So next step is nothing but the given problem is balanced or unbalanced assignment problem. Here the number of rows equals number of columns. So 4 rows is equals to 4 columns. So therefore the given the number of the number of rows is equals to number of columns. So the given transportation or given assignment problem is balanced assignment problem. So next observe. So this is balanced assignment problem. So now subtracting the smallest cost in each row from each element of that row. So this is clearly minimization problem and also square matrix. So first row, so in first row, so which is the least element? So first row is least element is 20. So 20 is the least element. So selecting 20 from first row and subtracting each and every element in that row. So 20 minus 20 is 0. So next 25 minus 20, 25 minus 20, 5. So next 22 minus 20, 1. So next 20 minus 28 minus 28. You know? So this is the 0, 5, 2, 8. So this is first row, subtracting. So next, so second row. Second row, least element is 15 is the least element. In second row, 15 is the least element. So subtracting each and every element in that row, 15 minus 15 is 0. So next, 18 minus 15, 3. So next, 23 minus 15, 8. So next, 15 minus, so 17. So 15 minus 17 is 2. So next, third row. So in third row, least element is 17. So 17 is the least element. So subtracting each and every row, each and every element in that row. So 2, 0, 19 minus 17 is equals to, so 17 minus 17, 0. So next 21 minus 17, 4. So next 7. So next last row, so D row. So in deep row, so 23 is the least element. So 23 is the least element. So 25 minus 23 is equals to 2. So 23 minus 23 is equal to 0. And 24 minus 21. So remaining 1, 1. 24 minus 23 is 1. So 24 minus 23 is 1. So this is the row reduction matrix. So this is row reduction matrix. So first, we have to verify the problem is minimization or maximization. So in case maximization problem, so we can convert minimization. So next after, Hello, sir. Completed, sir. Hello, hello.